Good morning, everyone. We're welcoming today Daniel Schaerer, who's going to tell us about the sources of cosmic reionization. And Daniel obtained his PhD in '95 at the University of Geneva before doing a postdoc at the Space Telescope Science Institute in Baltimore. And then in '99, he obtained the CNRS position in Toulouse. And after that, in 2002, he obtained the SNF professorship, SNF, which is the Swiss National Funds professorship, and he worked on the properties, the physical properties of the first generation of stars and galaxies. So he did pioneering work in stellar population synthesis models, including the prominent features in the spectra, first galaxies and stars, Lymanalpha emissions and helium-2 emission. And then since 2008, he's a full professor at the Department of Astronomy of the University of Geneva. And no, professor? You're not a professor?
Associate
it's
professor.
Associate professor. I don't know the difference, but yeah, professor. And so his, among other works, his expertise covers the properties of the first generation of galaxies using multi-wavelength observations and modeling. And this is all fine work, Daniel, but I think your biggest achievement was co-supervising my thesis, my PhD thesis.
Which was very hard.
Hard one. So let's listen to Daniel, who's going to tell us about the low redshift analogs of the sources of cosmic reionization. Thanks.
Okay, thank you very much, Hakim, for the introduction. And I'm happy to be here back at the IAP and talk to you about work we did with actually several colleagues who are here in the audience about Lyman continuum emitters. So in particular, Tuan was part of this work, Anveram, also Ivana. So I'll talk about Lyman continuum emitters, and first, of course, let me give you an introduction to a bit the topic, the questions we're after, what we know, and then what we've done in particular on low redshift Lyman continuum emitters, on their properties, and to put them in the big picture of what we think we know, and of course they also show some of the questions. So, of course, the very global introduction, I think you all know what we're talking about, so we're interested in trying to understand what are the sources which transformed the early universe. You know that we have simulations which put this in a mental picture and in a quantitative picture. So these simulations, like for example this one here from the Lyon group, allows us to show how the universe structure is formed, and the stars which are formed within these structures, how they transform the intergalactic medium, whose ionization fraction is shown here. And all this process leads, we think, within roughly 1 gigayear after the Big Bang to completion of the reionization. So we have several quantitative measures of this constraining the epoch of reionization and the change of the intergalactic medium. Of course, we have data from the Planck, from the polarization of the CMB, which gives us some indication. We have different measurements with different techniques, which I'm not going to discuss, which basically can be summarized in this figure, showing how we think the fraction of the neutral gas in the intergalactic medium has changed. And this is what we call the end of the epoch of reionization, which we think is basically happening or finished around redshift 6. And you can see here the available constraints now. Of course, there are a lot of ongoing efforts to try to measure this more quantitatively and more better, and the topology and a lot of other questions I will not discuss today. And one of the questions in this game is, of course, to understand which are the sources which have ionized the universe during this phase. Schematically, we talk about stars or quasars which could have contributed. And then there are different, more or less exotic explanations which are also discussed in the literature, but I don't have time to discuss all these options. Generally, we think that stars, so the sources in galaxies, have contributed most of the ionizing photons which reionize hydrogen, and quasars, higher energy photons, which reionize helium, which happens later around redshift 3 or so. So indeed, we have from very deep observations with HST and others. We have luminosity functions, so number counts of galaxies, such as this nice work here, which was done by Akim, which allows us to count as a function of the UV magnitude here, the galaxies down to the faintest levels. And this shows basically that at high redshift, so in the epoch of reionization, this is at redshift 7, for example, there are many, many low luminosity, low mass galaxies. And schematically, if you count all those galaxies and their UV emission, and you assume that roughly 10 or 20% of the ionizing photons which are produced by these galaxies, if they manage to escape the interstellar medium, then we have, if you integrate down to a certain limit, then we have enough photons to explain cosmic reionization. So this is why we think that galaxies are probably important contributors, but of course it's not a proof that they are doing this, because to do that you have to identify actual galaxies where the Lyman continuum photons can escape out of the galaxies, and you have to be measured to able, so how many escape is a number which we call the escape fraction. Then you have to be able to measure how many photons were produced or how many escape indeed out of the galaxy, and then you have to do the statistics, which is to fold this in with a luminosity density to see the cosmic budget of the ionizing photons. So there are different attempts going on to do this. I will show you in a minute that basically so far the searches for the sources where we see actually photons escaping has been very difficult and is still a difficult business, but there has been quite some changes and progress recently. And then, so there are a lot of questions on strategies, how to identify them and how to find them. And then I will also discuss how we can study the properties and what are the properties which we think which contribute, which make a galaxy having ionizing photons escape, etc. So let's first discuss briefly how we're trying to find Lyman continuum emitting galaxies. So there are basically different methods. Simply, we call them direct or indirect methods. The direct method in imaging, for example, is, simply if you have a galaxy whose redshift and here is the Lyman limit. If you have a filter which is well inside the Lyman limit, fine. So you just observe in this filter and in the other filters, and if you detect some radiation, then you have seen an image of the Lyman continuum radiation. This has been done for galaxies at different redshifts and with, for example, narrowband filters. But the difficulty is, and several candidates have been found where you see some emission in such a narrowband filter here, for example. The difficulty has been, and this has been identified a few years ago, is that in fact, if you observe with ground-based, from the ground, the resolution makes it that you can have a chance superposition of different galaxies which are in the same field, and basically this can mimic a source a source at a different redshift can contribute to flux in this filter. And indeed, all the candidates which have been turned up during several years or so, when people looked at them with HST in the UV continuum, in the Lyman continuum compared to the ground-based observations, no Lyman continuum detection was found in these galaxies. So in a nutshell, there were many candidates found with these ground-based imaging techniques, but most of them turn out to be contaminated by foreground sources. Then the direct searches for Lyman continuum emitters are also complicated by the intergalactic medium itself. As you certainly know, is that if we observe to increasingly higher redshifts, the Lyman forest, the Lymanalpha forest, absorbs a significant fraction of the flux, and basically renders the transmission or basically renders any direct observation of the Lyman continuum above redshift 4 or 5 or so impossible, or at least statistically very unlikely. So that means, of course, that at some stage we need to switch to indirect methods, because we will not be able to observe directly the Lyman continuum anyway. But anyway, so it's and this is what I'm going to talk about now in a few minutes. So let's see what indirect methods have been proposed. There have been several methods mentioned in the literature. For example, possibly peculiar line ratios of the optical emission lines of O3 to O2 could indicate Lyman continuum leakage. I will explain how this could work. My colleague Anwar Ham has, with simulations, proposed that the Lymanalpha line, the strength and its profile in particular, could show the escape of Lyman continuum emission. And then there has been also in the literature studies which said that the UV absorption lines, that they could be indicative of Lyman continuum escape. How does that work? For example, if we look at UV absorption lines, the idea is to say that if you have a galaxy whose interstellar medium is clumpy or contains certain lines of sight through which the UV radiation can escape directly, whereas other lines of sight are covered by absorbing clouds, then what you would see is the absorption lines, which are generally saturated, that those lines would not show a flux which goes to zero, because if you have a homogeneous medium, this would be completely absorbing. So this incomplete coverage of the UV light should in principle be a trace or an indication of a porous interstellar medium which could allow Lyman continuum photons to escape. So far this has been used in the literature a couple of times, but in fact people were kind of reluctant to use it and not convinced that it would work. We'll come back to this later because we think it is a method which can be used actually. As I said, Anveram proposed using radiation transfer models, proposed that this Lymanalpha line profile, which you can see here from predictions, either from a clumpy medium or from a medium which is completely ionized, that this would leave specific signatures on the Lymanalpha profile so that we would expect very narrow Lymanalpha profiles or double peak Lymanalpha profile in the case of in these cases, and that in these cases the Lyman continuum photons could also benefit from escaping. So this is a prediction which is very interesting and which, as you will show, we have tested and works indeed. The other very naive suggestion of an indicator for Lyman continuum escape is the following. It's simply related to a simplified picture of a H2 region. So suppose that you have a normal H2 region with a boundary, the Strömgren radius, then you know that in the inner parts you have a region which emits O3, in the outer parts you have O2. But now if the medium, if there is no gas anymore, or if the stellar population manages to ionize the whole galaxy, you are simply losing the outer parts of the region. Lyman continuum photons can escape, and what this would do is you would simply miss some of the O2 emission, and therefore the O3 to O2 ratio would be higher than usual. This is a very simple and probably naive picture, but anyway, it's interesting to see if that works. So now let's, in a few minutes, I just give you a quick overview of what has been done using these different techniques, but I don't think I need to spend much time on it. Sorry, these slides are a bit full of material, but there have been lots of efforts using these different techniques which I just mentioned. The bottom line, I think, from direct methods in spectroscopy or in imaging of Lyman continuum searches at redshifts 1, 2, and 3 or so on, has been generally that there have been very few galaxies found where Lyman continuum radiation is detected. Some candidates and many upper limits. For example, in these deep fields here, our colleagues from Italy have studied with very deep images with the VLT reaching 30 magnitude in the U-band. They have been looking for Lyman continuum escape in redshift 3 galaxies, and what you can see is that they basically have been able to determine only upper limits. So we have non-detections and upper limits, but in fact if you look at the numbers and the escape fractions limits they have, in fact these limits are really only constraining for fairly bright galaxies, whereas for the typical galaxies which we think would be really the dominant ones, these upper limits are in fact not so deep. But anyway, this is what these searches have mostly produced. They have also found some candidates and some galaxies which have been confirmed by looking at HST. For example, here, this galaxy here called IN2 has been found by Eros van Zella and studied by Stefan de Baus and others. And what you can see in this picture here is spectroscopic data and imaging, and here you have an image of the galaxy in different bands and in a filter with HST where you can see Lyman continuum radiation. You can see it also in the spectrum, and there is no indication for any other source sitting on this line of sight. So this is one of the best Lyman continuum galaxy we probably know, and it's situated around redshift 3, and we'll come back to that later. This is another example which has been found very recently by the colleague Rivera Thorsen and followed up by Eros van Zella. This is a spectacular, very bright arc, which I think was found actually following up Planck data. It's in a lensing cluster. It's an arc with many multiple images. Here you see the image of this arc stretched with showing different clumps. And this is the image in HST in the Lyman continuum. So you see multiple images of regions of a lensed galaxy redshifts 2 where you can see directly Lyman continuum radiation. But such sources are very rare and quite exceptional, or we have not found them. In spectroscopy, people have also been very active and have been able to turn up several candidates basically by using stacking. There is a detailed study from Jacques Steidel et al. Studying several hundred spectra with Keck. What he's finding is that in some subsamples of the stacks, you can find actually signal for showing the Lyman continuum here. And this similar study has also been done with VMOS, VLT, using data from the Woods survey. So we have some galaxies where we think we can detect Lyman continuum radiation. We can study the properties of the ionizing to non-ionizing radiation, but I think I'm not going to show this in detail. And most recently, there has been another study, which I just want to mention, where in fact the group of Richard Ellis or P.I. Robinson found among Lymanalpha emitters at redshift 3, they looked at 60 Lymanalpha emitters, and they have been able to detect 30% of those galaxies in the Lyman continuum with HST. So we have a few galaxies at high redshifts. What has been done so far at low redshifts or before 2016 could be summarized basically, or at least the detections could be summarized on this slide here. They were basically looking at very low redshift galaxies, so redshifts well below 0.1. There have been some detections where a very weak signal has been claimed, even with some detections and with HST, but really very few sources. And most importantly, sources with escape fractions which are of the order of 1% or less, which is not what we need to reionize the universe, where we were speaking, as we said at the beginning, of sources. The average source, if we want to explain cosmic reionization, needs to have an escape fraction of the order of 10% or so. So things have changed a little bit when a few years ago, with, as I said, with Anne, Tuan, Yuri, Ivana, and others, we sat together and said that we would simply like to try and test this very basic method of or suggestion of the O3 to O2 ratio, which could be an indication of Lyman continuum escape. And indeed, what we did is to follow up or to look at 5 galaxies selected for compactness, so they are green P-like galaxies, and for having a high 3 to O2. What was new is, in fact, is that we chose a very specific redshift range around 0.3, which in fact allows very efficient observations with the COS spectrograph on board the HST. And these are the galaxies we selected, so they are very compact in the SDSS images. Of course, we make sure that they are not AGNs through different diagnostic diagrams. And what was nice was that, in fact, the first galaxy Hubble looked at was a success. And here you can see the spectrum. So we were really surprised, positively surprised, of course, to see that there was a very clear, of the order of 12 sigma, detection of a flux in this continuum, which translates to an escape fraction of the order of 8%, absolute escape fraction of ionizing photons for this galaxy. Then we had another 5 sources. I don't remember what is actually this black curve here.
So what's the 12 sigma result?
This is the average flux in this band.
But it is above 0, and that black line, I think, is the interval over which we link the data. So the thing is that if there is no continuum escape, then you have a 0 flux. You are above 0, and you see the error bar, which is
Yes. So this is the flux measurement, and this is 12 sigma detection of a non-zero flux. Anyway, there have been other sources were looked at in the same run with HST, and in total over 2 HST programs now we have been looking at 11 galaxies. And what was very nice that in fact all the galaxies we selected, they show Lyman continuum escape. Here you can see some where it's much clearer. Here you see a very strong flux in the Lyman continuum here as well. So whereas the normal galaxy, if there is no escape of ionizing photons, you have a flux here of 0. So from all of those measurements, we can determine the escape fractions and a lot of other quantities. And what we basically found is that we have escape fractions between 2% and in the largest case of the order of 75%. We were interested in seeing whether possibly this escape fraction correlates with O3 to O2, because that, one could have naively expected this. So this is what we find. There is still some debate whether there is potentially a correlation with O3 to O2, although we think that there is a very big scatter and not really physically a clear reason why these quantities should correlate. What we now think in terms of a practical result is that apparently to use a high O3 to O2 as a selection criteria allows you to efficiently find Lyman continuum galaxies, but it does not allow you to predict the amount of escape fraction, of the amount of ionizing photons which escape. So what else did we do with these observations? We were interested in looking at the Lymanalpha profile, because Anverham had made these predictions of the Lymanalpha profile, which should be peculiar. And indeed, what was very nice was to see that indeed HST found peculiar Lymanalpha line profiles with double peaks or even triple peaks. And if you measure the separation between those two peaks, you see that it actually correlates very nicely with the Lymanalpha escape fraction. And basically this narrow peak separation is what was predicted to be a signature from the radiation transfer model. So this is a very nice prediction, a confirmation of a model, and it shows us, and we understand that it's related to low H1 column densities or a very efficient escape of Lyman alpha photons through holes, if there are holes. So this is in terms of empirical result, the best correlation we have so far, and which is an indirect measure of the Lyman continuum escape fraction if you do not have access to the direct measurement. We have also done other work on these galaxies, namely looking at the UV absorption lines, and I want to spend a few minutes going through this. So the basic idea was indeed to test different diagnostics, these galaxies. So we used the same sample of the Lyman continuum emitters, which we had found in the meantime. We have added other galaxies which are presumably non-leakers, and we've combined with looked at the UV spectra of those all from COS, and also compared this with other UV spectra from other galaxies. And the goal was to see whether we could study the geometry of the interstellar medium and to provide constraints on the covering factor, on the existence of channels or inhomogeneities or not, which could explain the Lyman continuum escape. So basically, to do that, you have to do some modeling of the stellar spectrum, of the UV attenuation and the absorption lines. You have to make some assumptions on the geometry, so either a picket fence or a uniform, and you have a distribution. You have to make some assumptions on where the dust is, and then for these different geometries you can write down the transfer equation, and you can fit the different lines and the spectra. Here are the different lines we are modeling. So we are modeling all the Lyman series lines, the O1 lines, and the oxygen 6 and silicon 2 lines, which people using or studying, or some people in IAP have a large experience with from the fuse and other times. So these are basically synthetic spectra which we generate for this spectral range. So Lyman alpha is on the blue side, and here we're really looking at the Lyman series. And then we are fitting these observed line profiles, and we are studying the different physical parameters. So here, for example, you can see just empirically a comparison of two COS spectra comparing one of our confirmed Lyman continuum emitters and a normal galaxy, more or less normal, comparable galaxy, which we think does not have a Lyman continuum escape. In fact, it does not have a direct measure, but we are anyway. So what you can see empirically, for example, here you can look at the Lyman beta and Lyman gamma line profiles or the regions, and here you see the same. You can see already qualitatively that in this object here, the lines are completely saturated, there is no flux, the lines are black, whereas in this Lyman continuum galaxy here, there is some residual flux in the lines which in principle should be saturated. So this probably empirically already tells you that there are some lines of sight through which UV radiation can escape, which probably also explains the escape of Lyman continuum radiation. Quantitatively, yes, we need to do this all the different fits. The fit parameters are the strength, the shift of each absorption lines, the column densities, the covering factor, and the stellar spectrum and the UV attenuation. And when you do all these fits, you can obtain interesting results. What you find is, for example, that the column density of hydrogen is fairly large. So it is of the order of 10 to the 16 in the lowest case, but generally more of the order of 10 to the 19, 10 to the 12, 20 to the 20. You can get also the hydrogen column density from unsaturated O1 lines, which are present in some of the lines, if you assume that you have the same metallicity in the neutral and the ionized gas. Anyway, the bottom line, what you find is that in these galaxies, there are high column densities of hydrogen, and these column densities are too high for the Lyman continuum photons to escape if the medium was homogeneous. So that means that there must be channels or holes through which the ionizing photons which we see escape. So this is probably the most direct proof we have so far of the way the ISM in these galaxies is shaped. And we can also determine the covering factor of different lines and compare them. Here you have a histogram showing the covering factors of the Lyman series lines from the leakers in this area here and comparison sample. And you can see that you can compare the covering factors of different elements. You find some possible differences, etc. So these are some technical effects I will not discuss further. There is an important thing which you should keep in mind and which has in fact kind of distracted people, I think, from using these absorption lines in the past, is in fact that if you simply use, as I was saying here, if you simply use the residual flux of these UV lines here to determine the escape fraction, which would be tempting. Here you would say the residual flux is 0, so the Lyman continuum escape is 0. Here it's of the order of 10–20%, so this would be the escape fraction. If you do that, in fact, it is not, you do not get the correct results. It's quite easy to see. It depends on the geometry and the radiation transfer equation, but basically the residual flux at line center does only trace exactly the covering factor, or 1 minus the covering factor, when there is no dust. In the other case, it is not exactly, you see the relation here, and you have to take this into account. So you have to fit at the same time the stellar spectrum and for the UV attenuation as well. And you have to explore different geometries if you want to compute properly, if you want to relate properly the residual flux to the covering factor, and then predict the escape fraction. And then I think we can skip that. Once you have done this modeling, you can compute the expected Lyman continuum escape fraction through this inhomogeneous interstellar medium. It depends on the assumption of the geometry you're making, on the distribution where the dust is, but in any case, for different geometrical assumptions, you can compute it, and you have just to choose the proper expression. And then what you find is these predicted values of the escape fraction, just looking at the absorption lines, and here they are compared to the direct measure we made by looking at the Lyman continuum. So the correlation is not perfect, but it seems encouraging to say that this method, with uncertainties, it can be used to determine the Lyman continuum escape fraction if you do not have access, if you cannot look directly into the Lyman continuum. So this is, I think, validation using this local sample, and we have also to check, apply this to some data which is good enough quality in spectral resolution and signal to noise. For example, a spectrum from a lensed galaxy, this cosmic horseshoe, where in fact people had looked before at the Lyman continuum with HST. This is a Lyman continuum image of this galaxy in HST, and they had derived a fairly strict upper limit of less than 2% of Lyman continuum escape. Now, if you look at these absorption lines, you see here that they do not go to zero, the flux. So people were kind of puzzled initially, and they said, oh, wow, this method does not work, because here you would expect an escape of 40% or so, if you naively translate the residual flux into an escape fraction. And therefore, people thought that this method cannot be used. But as I just showed you before, in fact, this method, it can be used. You just have to take into account properly the effect that dust is in this galaxy, and that all this has to be folded into the transfer equation. And if you do that with the method I just explained before, then you can translate this depth or this residual flux here together with the attenuation for this galaxy, which is non-zero, and what you find is an escape fraction which is less than 1%. So compatible with what is determined by these HST observations. So this is, okay, just one other case where we've played this game. It seems to be compatible and therefore promising. We don't know how well it will work in the end, but I think it gives us some hope or some idea that probably this method can be used. The only thing you have to be careful with is that you cannot simply just measure the spectrum and transform the absorption depth or the residual flux into an escape fraction. You have to do some quantitative modeling. And we'll see how well this method can be applied, how well it works. But I think it is a promising method, and which will also be interesting to do, for example, with 30-meter telescopes where we can get decent signal-to-noise spectra in the continuum. We are using it, for example, now with the Vandal survey, where we have 80-hour spectra taken with the VLT of galaxies between redshift 3 and 5. So you have really high signal-to-noise spectra in the UV continuum. And of course, the James Webb can also observe some of the brighter galaxies in the continuum. So maybe this will be a useful method anyway. So I think, just to summarize this part here, I think we have studied now a certain number of indirect probes, and I think we have some handle on how we can connect direct Lyman continuum and measures of the Lyman continuum escape fraction with some of these indicators, with Lymanalpha being the one which correlates best with the Lyman continuum escape fraction, but other indicators being useful either quantitatively or also to allow to pre-select candidates. And I think this is very important and a good timing, let's say, for James Webb and the ELTs, which will soon come as well. Now let's see a little bit more about the galaxies and their properties themselves. I've mostly discussed about the methods, how to find them and how to measure the amount of Lyman continuum escape. Let's briefly talk about what kind of galaxies are these actually. What do we know about them, and how does that fit into the picture we have? So first of all, the galaxies we looked at are, as I said, by selection compact. We selected them to be compact, basically because we wanted them to be completely included in the COS aperture, and because these were among the galaxies which had the highest O3 to O2. But so this is a property by selection, and other properties we can derive for these galaxies are basically everything or nearly everything we want. These are selected from the Sloan, there are images, there are spectra, there are deep spectra, so we can basically measure stellar population, stellar masses, metallicities, extinction, etc. with the usual methods. And the bottom and the main results of this ensemble of 11 galaxies which we studied is summarized here. The spectra of these galaxies from the UV to the optical are dominated by very young stellar populations. This is again a selection effect. We've selected for galaxies which have very strong emission lines. These galaxies have fairly low stellar masses of the order of 10 to the 9 or so. They have very high or fairly high star formation rates, so they are at redshift 0.3 or so. These are the star formation rates, which means that the specific star formation rate, the star formation rate per stellar mass, is fairly high. They are low metallicity, but not extremely low metallicity. They have a relatively low extinction, etc. And we'll see how this, we will see in a minute actually that this kind of properties is more or less what we think is a very common property for high redshift galaxies. We can also say something about the UV attenuation law. This may interest some persons here, because there is some debate on what is the typical attenuation law of star-forming galaxies at high redshifts. So in the case of our leakers, we basically can measure everything from the UV to the optical. You can measure Balmer decrements, etc. And from the knowledge of the stellar population, you can see that in fact you need basically very steep attenuation laws to describe these galaxies, laws which are as steep as the SMC law and significantly steeper than the Calzetti law. Whether this is a general property for young galaxies or metal-poor galaxies or so, some people are discussing that or debating that, I don't know. We can just say empirically that these leakers which we looked at, they all have this kind of attenuation law. And this may be interesting because there is some debate on the high redshift end on what is the correct attenuation law, etc. Anyway, just to show something we can learn from these galaxies. Then an important quantity which we can derive is the amount of ionizing photons which are produced. Because as I said, for the budget of ionizing photons to explain cosmic reionization, we need to know not only how much escapes, but I mean what fraction escapes, but we need to know how much in absolute terms is produced of ionizing photons are produced. And this is a quantity which is now described by this kind of weird quantity Xi ion. It's basically the number of ionizing photons emitted by a galaxy per UV luminosity. So per UV at 1500, for example. And in normal calculations for the budget of ionizing photons, we usually assume this value here, which is 25.2 here on this log scale. And what we've seen is that in the galaxies we're looking at, we have a somewhat higher ionizing photon production of the order of 2 to 5 times or so, or at least somewhat higher. And this is related to the fact, compared to the standard assumption here, can be easily understood by the fact that our galaxies contain mostly fairly young stellar population which emit more ionizing photons per UV. So this, if this was typical of all the galaxies, of course it would make life a bit more easy to explain cosmic ionization. But we don't know yet whether this is typical for the high Z galaxies, of course. Now let's step back and compare these galaxies with higher redshift galaxies to see how that fits in. And of course the first thing to look at is to look at the best Lyman continuum emitters we know at other redshifts. So for example, go back to this redshift 3 galaxy which I introduced before, which is called IN2, and which in fact, as I briefly mentioned, was found by looking at the Lyman continuum. So these were found from imaging the Lyman continuum, and then people, Eros van Gella, went back to study all the different properties of these galaxies to obtain spectra, etc. And what is interesting is to see that so this single galaxy here, this best, let's say, redshift 3 Lyman continuum leaker, has in fact a metallicity of the order of 1/6 solar, a stellar mass of the order of 10 to the 9, which is exactly the same as our galaxies. It also shows strong Lymanalpha. And if you obtain with X-shooter, you can obtain the O3-2 ratio. You find that this galaxy has also a high O3-2 ratio and high equivalent widths. So a posteriori, you find that this galaxy here has more or less similar galaxy properties to the ones we were studying at the low redshift, at redshift 0.3 or so, which was selected in a completely different way. So whether this is, of course, a universal conclusion, that means that all Lyman-containing galaxies should have this kind of properties, this is, of course, a step we cannot yet take, but it's at least interesting to see that they are comparable and that you can find comparable galaxies by selecting them in different ways. Here I show an illustration of the strengths of the nebular emission lines, which you've seen previously of our galaxies. In fact, if you look in the photometry, our galaxies from the SDSS, they look like that, which is what makes them, which makes some of these galaxies be called green peas, because they have an excess flux in some of the filters. In fact, what is interesting is to look at quantitatively what is the equivalent width of these galaxies. So they really have high equivalent widths. Here the O3 lines, for example, have 1500 angstroms of equivalent widths, etc. But fine, so this is peculiar for low redshift galaxies. But in fact, when we look at high redshift galaxies, at least what we can study so far before the James Webb is flying and will directly measure these equivalent widths and line strengths in spectroscopy, what we know so far from high redshift galaxies is photometry. And in fact, at redshift, here you have an example of a galaxy around redshift 7.7 or so. At high redshift, we consistently see this kind of strange photometry here in Spitzer bands, which we think can only be explained by very strong O3 and H beta lines. And in fact, if you look at compilations of data which have tried to measure the strength of the emission lines in galaxies at different redshifts, you can summarize them in these kind of plots. For example, here you see compilations of data where we try to follow galaxies over a certain mass range here at different redshifts, from redshift 0 to the highest redshift, and people are trying to measure the equivalent widths of the H beta and O3 line, which we can do by photometry in most of the cases. So what one finds consistently is that the equivalent width of this line and also H alpha here increases strongly when you go to higher redshift. And in fact, the equivalent widths, which we think is typical here for galaxies in the epoch of reionization, or here, so above redshift 6 or so, this value here is the value we find in our Lyman continuum leaking galaxies at redshift 0.3 or so. So as you can see at redshift 0.3, where we are looking at, the normal value is very low. So our galaxies are really freaks, extreme rare galaxies in the local universe, but all the properties we've measured from those galaxies, all the properties I could mention so far, in fact, they indicate that these properties are typical for those of high redshift galaxies. So here I only show the equivalent widths, but if you look at stellar mass estimates, star formation rates, etc., from high redshift galaxies, in fact, they are very comparable to those of our galaxies. And therefore, we say that we have probably the best, or at least the best, analogs of the sources of cosmic reionization we know so far. Now, what do we think? So, okay, now it's time to wrap up a little bit. What do we think? What are the common properties of the Lyman continuum emitting galaxies? In a nutshell, or to put it all together, we think that the galaxies which are compact, have a young stellar population, are strongly star-forming, show a strong Lymanalpha line with peculiar profiles, and have a high O3 to 2 ratio, that these galaxies probably show a strong Lyman continuum escape fraction. We think that the way this escapes, the Lyman continuum photons escape, is through holes or channels in the interstellar medium, and these properties here are consistent with the high redshift observations we have so far from spectroscopy and observations. All of the leakers, they basically show these kind of properties. Now, what is really the physical property which determines that these galaxies have Lyman continuum photons escape out of their interstellar medium? We do not really know. So far we suspect that it may be the fact that these galaxies have a very high surface, have a very high star formation rate per area, so a very compact star formation going on, a very intense star formation going on in a very high, over a very compact region, that this may trigger peculiar conditions or blow holes or channels in the interstellar medium and make these galaxies have these holes. So this is a plot showing as a function of redshift, or trying to compile the star formation rate, the surface density for galaxies which are either confirmed or possible Lyman continuum leakers. And here are our low redshift galaxies, and these are a few other galaxies. IN2 I was mentioning here. But this is a possible hint that this quantity here could be relevant for determining the fate of a galaxy. This remains to be seen, I think, both from the modeling side, from observations. Of course, we need larger samples. There is a large HST program going on right now at this redshift here, spanning a very large range of physical parameters, different SFR surface areas, sigma SFR values, and different physical parameters. Hopefully we will know soon what are really the physical parameters which determine the escape of the ionizing photons. But basically we think that we have the following picture, is that there exist Lyman continuum leakers at low redshifts, that the production of ionizing photons increases when we go to higher redshifts. This is a compilation of different measurements which we can do by measuring basically hydrogen recombination lines, so H alpha, and the UV luminosity, so we can basically determine, at least with some uncertainties, that overall trends of the ionizing photon production. We think that this quantity correlates also with other observable properties, for example, the strength of the oxygen 3 lines, and that possibly, as this work here from Tang and Stéphane Charlot and others suggests, that possibly the production of ionizing photons could increase when you go to more extreme objects with stronger equivalent widths. This is something which is plausible and which would be quite natural because this can be simply related or due to average properties of stellar populations which are younger and which go to lower metallicities. So if the photon production increases slightly with increasing redshift, this is good to explain cosmic reionization. Then how much of those escapes is another question. I already showed that maybe the escape is related to O3202, and the higher O3202, the higher the chance that you have escape of ionizing photons. There are indeed some data suggesting that the objects with higher and higher equivalent widths of O3, that they have also higher O3 to 2 ratio, and therefore if this is somehow proportional to the escape fraction, this could also increase, and as I showed, this quantity here increases when we go to higher redshifts. So I think all of these studies so far indicate that we do not have a problem of explaining cosmic ionization. We now have found a certain number of Lyman continuum emitters, and we have certain properties which we can measure and quantify, and all of those match and fit together to show that basically the average galaxy at high redshift is probably in a good situation or in conditions which are similar to those we have seen, i.e. that they could emit a significant fraction of ionizing photons. And if you put all these things together, so the evolution of the ionizing fraction of the ionizing photon production with redshift, some empirical model of galaxy formation, and some assumptions on the escape fraction, then you can come up now and in the recent years with models which can successfully explain the evolution of the IGM neutral fraction with redshift here. This is from a recent model from Naidu et al. Showing that with different model assumptions, one can roughly reproduce this observed constraints here. They think that this one can also exclude, for example, some models here like this one, which suggests that very low mass galaxies dominate, etc. But there is a whole debate on still exactly which galaxy contribute how much. And yes, I can refer you to those papers here. This is certainly at the front, but we think that we have enough galaxies potentially, and that when you go to high redshift, the conditions, the compactness, the star formation rate, intensity of these high redshift galaxies makes it that probably a significant fraction of them are going to have a leakage of ionizing photons and therefore contribute to cosmic reionization. So I think it's time to wrap up. So here are here's my summary slide. I think we talked about the recent detections of Lyman continuum galaxies selected by O3202 and compactness. We've discussed the properties of those galaxies, the metallicities, the star formation rate per unit surface. I think a quite important part of this work was to show that we can use indirect methods to detect Lyman continuum galaxies, and in some cases, in particular, using the Lymanalpha line, also to measure or predict quite accurately the escape fraction of the ionizing photons. And I think I've convinced you that these galaxies are good analogs of the sources of cosmic reionization, and I think I'll stop here and take your questions.
Thank you, Daniel. Questions, Susanna?
So, sorry, Daniel, you didn't convince me on the last point, in the sense that You say that the galaxy you study at low redshift have similar properties as those like ion 2 or the one at redshift 6 point something, but those are not the average galaxies at the epoch of reionization, because the bulk of galaxies at the epoch of reionization is way much fainter than these ones. So my question is, are just the brightest, or some of the brighter galaxies that will be able to make the reionization, or do you expect that you have also this bulk of galaxy population at the redshift that has also similar properties, let's say in ionizing factors, and that is contributing to the ionization? Because the galaxy you show, ion 2 is extremely bright galaxy, and the one at redshift 6.7 are those that are able to study today that are also way brighter than the bulk of the galaxy population at very redshift.
Yes, sure. I mean, we know, I have no time to go, we know that that there is a whole range of the luminosity function which we are not probing right now. So indeed, we are looking at the relatively bright end of the UV luminosity function now. So that's all we can say, is that it's the same in for example, this mass range here, where we can probe the properties of galaxies across a significant fraction of cosmic time. And so these galaxies exist, and they exist at high redshifts. So all what we are saying is that this, you can say, tip of the iceberg of galaxies at high redshift here, that they have properties which look like the Lyman continuum leakers we can see. So it only tells you that this part here of the high redshift galaxies has properties which are comparable to the leakers we see now. Of course, we do not know yet the properties of the fainter galaxies at the high redshift end, because there is a whole range of the luminosity function which we need to probe. And indeed, in terms of number, they are very numerous. So we do not know yet what they are. But we see that these galaxies are all very compact, and we can measure, I mean, most of the time they are even unresolved. So we know that they have also a very high staff mesh rate per unit area. So this is a quantity we can compare. But indeed, we cannot yet compare the properties of our galaxies with the faintest and most numerous galaxies in the epoch of reionization. That's for sure. All we can say is that those which we can already compare with at high redshifts, they have exactly, or basically exactly the same properties as the leakers now. Now, whether the bright end of the luminosity function dominates the cosmic reionization or the faint end or whatever, I think this is still an open debate. And maybe you have some specific opinion on this Naidu paper or others, but I think this is still work to be done.
They can dominate and be enough,
yes,
to reionize.
With some assumptions and modeling, they seem to be able to dominate, but I think these are things which I mean, this is really one of the things for which the James Webb is built, I think, and which it will do. It will measure escape fractions and will quantify, galaxies down to much fainter levels than we know so far, and so. But we can speculate for now. I think what we can say is that with not completely crazy assumptions, we have enough photons to reionize the universe with galaxies. I think this most people would agree on.
Thanks, Danielle. That was very nice. I have a question about the clumpiness of it. So the clouds are dusty in your fits, right? Because you have an EB minus V of 0.16, for example, and whatever the one you showed. So I'm curious about the relationship between NH1 and the EB minus V for the dusty clouds. And then the other thing is, have you actually thought about doing high resolution ALMA observations to try to see that dust emission and try to get at the covering fraction in a direct way?
Okay.
That would be an emission, because that will help you break the degeneracies also between EB minus V and a lot of other things in the modeling. Yes,
I don't know which figure I should really show here. Indeed, we do not know we do not know what is the distribution of dust. We just have to make some assumptions, and right now we're just using these very simple models here, which probably are both okay. But you have a idealistic.
Integrated NH1, right? In a
Yeah, we can give you the ratio of EV minus V to NH. It shows large scatter, and some values are much higher than galactic, and so on. In fact, yes, this is all we can do I think for now. For what you're saying, for the distribution and for measuring the dust, the distribution and the gas and so on, this is indeed a quantity we would really like to do. We've been putting in ALMA proposals already, I think, 2 years ago to target some of the galaxies. In fact, we did obtain some NOEMA observations at the beginning of 2 of our leakers. They were non-detected. And then the bottom line of the ALMA proposals is that in this period here, we got a proposal accepted. So ALMA will look at, I think, all the leakers which are observable from the south. But for now, from our non-detections which we have from NOEMA, we are basically going for a detection experiment. So it seems to be difficult to detect and resolve and really study at a very high resolution. Ideally, of course, this would be great. I mean, the first obvious thing would be, to get an image at a HST resolution with in 21 centimeter, or better resolution to see the holes in the H1. Of course, everybody or people who are looking at radio, they know that this is not possible, and this is maybe even not completely trivial when we go to the SKA period. So we do not, it's still beyond the possibility to measure the integrated hydrogen column density directly from 21 centimeter and to get images and to resolve it is we're not yet there. But so I think we have to live with these simple sketches and so on, and but there are, of course, there are a lot of simplifying assumptions which are questionable.
Yes, nice talk. Well, we know some of these local analogs produce also X-rays, and there is increasing evidence that the X-ray flux as a function of star formation increases with redshift. What is, in your opinion, and how would you compare the incidence of the X-ray flux of these galaxies in the reionization epoch of the universe?
Yeah, I have not thought a lot about this. I think in terms of the concrete samples of Lyman continuum emitting galaxies we know so far, I think there are not many, or maybe even none of them has X-ray observations. Some people are starting to look now, and there have been some papers, I think Ivana participated in one, looking at the X-ray properties of green P galaxies, which are the properties of this kind of galaxies. I don't think we have a clear picture on whether they are normal like other galaxies or peculiar. And then there is a whole debate, but you know better about how important the contribution of X-rays can be to the heating of the IgM and so on in the early universe. I do not have a very strong opinion on that, but it's certainly interesting to try to connect and understand how these X-ray sources, which can be present in some of those metal-poor galaxies, if and how they would alter the ISM or even contribute to blowing holes or changing the radiation field. And so I think we do not know much about this yet.
Yeah, you made a very convincing case of the ionizing photon coming from massive stars. But a few years ago, there was a paper by Madao saying that AGN may contribute a lot to ionizing photon. What is happening to that idea now?
Well, in fact, there has been yes, there have been different times claims that there should be more AGN than previously thought. I think there has been still back and forth. The candidates or the galaxies, the AGNs which were proposed by Jalongo and Madao or a few years ago, they were basically scrutinized and they turned out to be not at the right redshift. And so I think there has been a whole debate. But I think that the people have over the last 2 years converged to many of those suggested AGN not being at the right redshift or being not AGN. So I think right now, but I'm not an expert. There seems to be a kind of consensus that there are not so many AGN, that the luminosity function is decreasing, or the number density of AGN is decreasing quite rapidly. But I'm not sure. Maybe some people know better. This pops up. This topic pops up every few years, and then somebody says yes, but there we find more. So maybe maybe, I mean, I don't think we should completely exclude their contribution and so on. What we are trying to do is, okay, as you know, is to advance from the galaxy side, to look at the galaxies and see, you know, can they contribute and how much and so on. I think it's complementary, and we have to see if and to what contribution AGN can play exactly.
Hi, Daniel. I would like to go a bit beyond Susanna's point. And it's not a question only of flux, it's a question of surface density. So if you go at high redshift, of course you can try to cope with the lower limits in the luminosity function, but what really matters is surface brightness. And surface brightness at high redshift will be affected by cosmological dimming. And so those galaxies will not be detectable, and they may be the main source of cosmic ionization. And at the moment, we don't have instrumentation to actually cope with them. And if you go at low redshift, what we show is that the leakers actually have high surface star formation rate per unit area. Well, this is called surface brightness. So you're just looking at the very bright objects in surface brightness, and you're detecting them. So I think my feeling is that if you go at low surface brightness, you will see, again, Lymanalpha extended emission, and Lyman continuum also emission. So my point will be try to go deep, not in flux, but in surface brightness. And then you will be detecting that most galaxies actually have a very low covering factor and very high escape factor.
Yeah, I'm sure. I mean, I agree on the first part that we should explore a wide range of parameters. So not only look at compact galaxies, whether we're going to find escape from all of them, I'm not sure. I mean, at least every galaxies which has been studied previously with hard fuse, HST, etc. in the nearby universe, people have found basically zero escape from looking at normal galaxies.
But that's biased by the luminosities, luminosity weighted. It's not the total number of financing photons.
Well, but they are looking at UV bright regions in certain galaxies. So I think if you're saying everything comes, I mean, if the UV flux is dominated from a diffuse region and you never observe it, then I agree with this. Anyway, it's a possibility that one has to, and certainly I think everybody is aware that we do not understand. I'm not saying that all the galaxies are like that. We are saying that by looking at compact galaxies, we have found galaxies. It was a challenge so far to find them, but it's not to say that the whole universe or all the leakers are restricted in this area. So right now, in fact, this HST large program I was mentioning is precisely trying to explore a wider parameter space. So move away from the single selection, change the selection criteria, and explore different parameters and see whether we still find this Lyman continuum escape, and if it becomes higher or lower or whatever. So I think we still have to explore, and it's certainly the low surface brightness, certainly interesting, but it's not the easiest way.
I have a quick question.
Just again to follow basically excellent point. I mean, do those new use observations of Lymanalpha around halos at z=2 change the game a bit on that, and do the new models take into account that? At very low, now that you have like low surface brightness emission in halos, I mean, could that contribute to? Just a very dumb question, probably.
I mean, to have a diffuse Lyman-alpha emission, you do not need to have it does not imply that the Lyman continuum photons escape, because Lyman alpha, once it's produced, it can scatter over wide areas. Now,
the H1 content of those halos is tiny. So.
Yeah. I have to think about the connection with your question. Yes.
I think we should wrap up, and thanks, Daniel, again.
Okay, thank you.